Hey everyone, welcome back to my journey of water-based suffering. The first video did way better than I expected, so now I'm contractually obligated to keep going. It's been a ton of fun making these videos and a great way for me to step away from this insanity from time to time, so I guess we're doing this for real now, there's no turning back. Last time, we managed to get the fluid simulation working with some colored debug boxes. Today, we're taking things to the next level. After we look into more optimizations, because this 3 FPS animation is going to make me crash out.
Julian!
But before we get into it, a quick moment of silence for my GPU, which has been through a lot lately. Since the last devlog, I've been doing what any reasonable person would do when faced with a complex programming challenge.
See, as you can see, the more you fuck around, the more you're going to find out.
First, let's have a look at where we left off last time. Beautiful, right? Looks exactly like water, if water was made of blue Lego pieces. This is peak game development right here. I mean, technically it works, but aesthetically it's a disaster. It definitely has that my first programming project vibe. Like when you're so proud of making something work that you don't even care, it looks like it was made in MS Paint. So the first order of business was more optimization, because my computer was about to achieve liftoff. I started with implementing multithreading using Unreal Engine's Parallel 4. Here's the basic idea. Instead of computing each voxel's behavior one after another, we split the grid into chunks and calculate multiple voxels simultaneously using different CPU cores. In theory, with 8 CPU cores, we should be getting up to 8 times the performance. In practice though, well, the challenge is that our water simulation often requires each calculation to know about the results of nearby calculations. It's like trying to build a house where each room needs to know what the adjacent rooms look like before it can finish being built. This creates dependencies that can force threads to wait for each other. I have a feeling that something is still locking my threads here, but in order to find out, I'll need to write benchmarks and run traces using Unreal's insights properly. But that requires understanding what insights is actually telling me, and right now it's like trying to read hieroglyphs. Is this good? I generally don't know. Is line going up? Is that good or bad? Why is everything red? What's a hitch? Why do I have so many of them? Next up, it was time to improve our simulation calculations. Originally, the complexity was at O(n cube. When we have n voxels in our simulation, O(n cube means that for each calculation step, we might need to perform operations proportional to n cube. So if we double our resolution, going from 32 by 32 by 32 to 64 by 64 by 64, our calculation time doesn't just double or quadruple, it increases by a factor of 8. This is the kind of inefficiency that makes computer science professors wake up in a cold sweat in the middle of the night.
No, 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 no! Wait!
So I rewrote the linear solver to reduce complexity and bring it down closer to O(n), ideally. Of course, ideally in my case is like saying in a perfect world where bugs don't exist and everything actually works. What this means practically is that instead of checking how every single voxel might affect every other voxel, we're now only considering nearby voxels that could actually impact each other. Because, let's be honest, water on one side of the pool doesn't care much about what's happening on the other side until the waves actually reach it. Alright, with that out of the way, I also implemented an adaptive timestep algorithm that automatically adjusts based on the CFL condition. And by CFL, I mean this. This calculates the maximum safe timestep based on the fluid velocity. Basically, it prevents the simulation from exploding when the fluid starts moving too fast. The code finds the maximum velocity in the grid, then uses the formula timestep equal safety factor times cell size divided by the maximum velocity. With the fixed timestep, water sometimes moves too quickly, simulation breaks, everything's on fire. With adaptive timestep, water moves at physically plausible speeds, my GPU gets to live another day. For now. Starting to understand why people don't tackle this problem much, or if they do, they don't really talk about it. The deeper you go, the more you realize how much you don't know. It's like pulling on a loose thread and suddenly your entire sweater is gone and you're just sitting there naked, wondering where it all went wrong. So obviously, the next logical step was to pretend like I know what I need to do and go back down the rabbit hole and dig into more algorithms. I really wish I had paid more attention in math class, but now it's too late. What's a conjugate gradient method, you ask? Well, I had absolutely no idea, but the internet told me it would work faster. According to Wikipedia, it's an algorithm for the numerical solution of particular systems of linear equations. Let me try to explain this in English. In fluid simulation, we're trying to solve pressure equations across thousands of voxels all at once. That's a massive system of equations. The naive approach would be solving each equation one by one, but that's painfully slow. The conjugate gradient method is like taking a smart shortcut. Instead of checking every possible path to the solution, it follows the steepest path. Imagine this surface represents our error. We want to reach the lowest point, the solution. The conjugate gradient method is like rolling a ball down the steepest path, but with a special ability to remember previous directions to avoid zigzagging. In practice, this means we can solve our pressure field in maybe 20-30 iterations instead of thousands. Here's a little snippet of the actual implementation in my code. And finally, the multigrid solver. The multigrid method is like solving a puzzle by first solving a simplified version of it. It creates a hierarchy of grids, different resolutions, solve the problem of the coarsest grid, then gradually refines the solution. It's the computational equivalent of looking at the problem from far away first, and moving closer, and it's ridiculously efficient for a pressure projection. The implementation calculates how many grid levels we can use based on the simulation size, then performs V cycles, smoothing the solution at each level, calculating the residual error, and restricting it to a coarser grid. Solve at the coarsest level, where the problem is much smaller and easier to solve. This hierarchical approach makes convergence much faster for larger grids. What would take hundreds of iterations with a standard solver takes just a few V cycles with the multigrid. I should probably mention here that we're moving further away from an actual fluid simulation and into more of a fluid approximation. Otherwise, this will never be usable at scale in an actual game. I'm still not sure if it ever will, but at this point I'm in far too deep to give up. These algorithms being implemented is only the first step. Next, I'll have to write some benchmarks and figure out what combination of parameters yields the best quality performance balance. But that's a problem for future me. No, I'm not procrastinating, I'm simply waiting to be older and therefore wiser. Okay, so about 3 codings later, this is where we are. We now have multithreading, octave optimization, adaptive and fixed time steps, faster solver with multiple algorithms. I've also added more debug views, including density, slopes, velocity visualization, added a way to control the fluid source and editor, so now we can move the source freely, toggle it, adjust the strength and density. It's like playing God, if God was really bad at programming fluid dynamics. Then I kinda got sick at looking at these debug boxes, not to mention that I still had no idea how this would actually look like when rendered, if it would work properly, or I had messed something up and wasted 3 months of my life. So I thought, how hard could it be to implement a renderer for this? I decided to look into the marching cubes algorithm, which is pretty much the standard for rendering volumetric data like our fluid simulation. Imagine we have our 3D grid of voxels. Each corner of each voxel has a value representing how much water is there. A value above a threshold means inside water and below means outside water. The algorithm examines each cube in our 3D grid by looking at its 8 corners. Based on which corners are inside or outside the water, it generates a specific triangle configuration to represent the water surface. There are technically 2 to the 8 So 256 possible configuration for how water could intersect the cube, but through symmetry these can be reduced to just 15 unique cases. For each cube that contains both water and air, we place triangles that approximately follow the boundary between them. When you do this for the entire grid, you get a smooth surface. The beauty of this algorithm is that it creates a continuous mesh that looks smooth, unlike our blocky debug view. It's basically how most games render water, smoke, clouds, and other volumetric effects. And after a few, and by a few I mean a lot, of failed attempts, wrong world coordinates, wrong UV mapping, a lot of wrong things, I had something passable. Here are some of the fun issues I encountered. Inverted normals making the water look inside out, z-fighting or triangles overlapped, weird seams between chunks of the mesh, and water appearing completely detached from the simulation. As it turned out, I had 3 different coordinate systems fighting each other. The grid coordinates, so 0 to grid size -1, voxel world coordinates, the position in our real world space, and the vertex coordinates for the mesh. Getting these 3 to play nice was a nightmare. It took me forever to make sure the coordinates of the render matched the simulation. But then, I eventually got it. This render is still super scuffed, but it's nice to have for now. And I'm still working on performance optimization, and it's nice to have confirmation that our approximation still behaves the way we want it to. The next steps are to work more on the simulation and implement some logic for fluid accumulation, so our fluid actually fill up spaces, settle, and get closer to what we're looking for. Currently, the simulation works well, but it doesn't quite accumulate and settle like real-world water. It's like having a water balloon that never settles into its container, it just kind of exists. I want to get it to the point where it can actually fill up caves and create pools of water that behave realistically, you know, like actual water. The bare minimum of what I set out to do about 500 hours ago. I also need to improve the material on the water itself. Right now, it's just a basic blue material with some transparency. I want to add proper refraction, reflection, caustics, foam at the edges, and all those nice water effects that make it look less like blue jello and more like actual water. But one step at a time. First, let's make sure the physics actually works before we worry about making it pretty. So that's where we are so far. From some color debug boxes to something that almost resembles water if you squint really hard and maybe have had a few drinks. Is it perfect? Absolutely not. Does it run without setting my computer on fire? Most of the time. Is it still rough? Yeah, but it's getting better. And that's what we call progress. I was ready to give up multiple times during this process, but we pushed through it. The work continues. My sleep schedule is destroyed, my friends think I've disappeared, and I've become that person who brings up fluid dynamics in random conversations. If you enjoy watching me struggle with math I barely understand and yapping about algorithms that are melting my brain, make sure to like and subscribe. The support really does help a ton. Drop a comment if you want to see more of this chaotic journey. I'm literally learning as I go, and it's kind of amazing how much I don't know what I don't know, but I'm having a ton of fun doing it. Next time, hopefully making the water actually fill spaces and look even more like water. But knowing me, I'll probably end up spending 3 weeks implementing some obscure algorithm I found on page 94 of a research paper from 2005. This project is taking over my life, and I'm starting to see fluid simulation when I close my eyes. Catch you in the next one, and stay hydrated. Get it? Because water? I'll see myself up.